the organizers. So thank you for giving me the opportunity today to share from my screen right now. Oops, I hope you will be able to see my presentation. Okay. So we talk about the silicon and germanium-based composite for the development of battery electrodes. So I apologize for not being with you in person due to some delays. I've been facing obtaining my visa, but I hope we'll have the chance to meet in person pretty soon. So I hope you can listen to me very well. I hope so. So the work I will present today will focus on the electrochemical synthesis method that we have developed in the lab to create a variety of nano-objects and nanostructures. And the goal is to address various applications related to optics, but also in the field of batteries, which is the focus of my presentation today. This work has been done in collaboration with many persons, many collaborators in the LRCS lab in Amiens, and also the Electrochemical Energy Storage Network and the ADEN, which is a French agency regarding many topics related to environment. So the outline of the presentation will be as follows. So please feel free to interrupt me if you have any questions or if anything is unclear. So I will, because some of you maybe are not familiar with electrochemical energy storage, so I will start my presentation with a very brief introduction to various energy storage systems with a focus on the electrochemical energy storage. I will then discuss the challenges of lithium batteries, and particularly the negative electrodes, which are fundamental for my presentation. In the second part, I will present to you the different electrochemical synthesis method that we have developed over the years in the lab. Through a few examples, I will focus specifically on the organic anodization and structuration of titanium dioxide, and also on the electrodeposition in ionic liquid of different materials such as silicon germanium and silicon germanium aluminum alloys. Finally, I will conclude with practical applications focusing on lithium-ion batteries, particularly those concerning negative electrodes, and I will give you some recent results and future perspectives. So to begin, I would like to briefly compare the different energy storage systems using a Ragon diagram. This type of diagram represents specific power on the y-axis and the specific energy, watt-hour per kilo on the x-axis. The value of the Ragon diagram lies in its ability to visualize quickly how a system can store or deliver electrical energy. So we have those lines, or maybe I should use my laser pointer, sorry. So we see on the diagram, so here on the y-axis we have the power, on the x-axis the specific energy, and it gives us the ability to draw those lines, and it shows how fast you can store or use the energy. So we see, for instance, on such diagram that supercapacitor, which are just here, have very high power energy, so rapid charge or discharge, but very low energy density here. Reversely, for instance, fossil fuels present very high energy, but quite low power. Lithium-ion batteries are right in the middle right here, so it's very good compromise. It's a good balance because mainly for the lithium-ion batteries, due to the size of the lithium, which is very small atoms, which can diffuse very quickly in the electrode materials, which gives us a very quite good specific energy, and also this fast diffusion gives us a very good power energy. If we compare the different energy system, so here we have pumped hydroelectric storage, compressed air energy, flywheel, for instance. We see that for batteries, the energy range is pretty large. We have a good balance between, again, the storage energy and the power. We have a quite low carbon footprint. However, we still have a lot of challenges, which is not, for instance, the cycle life. So lithium-ion batteries, although not having the largest storage capacity, provide a good balance of the stored energy, because it is also very versatile compared to many other devices. So to give you a very short principle and basics of lithium-ion batteries, so the principle is very simple. So it is based on four main components. For battery, we have a negative electrodes, usually graphite. The graphite is just right here. And we have a positive electrode, mainly on the commercially available battery. We have cobalt dioxide lithium. We have an electrolyte containing the ions and a separator, which is usually polypropylene, that prevents the short circuits between the electrodes. During charging, the external generator applies voltage across the electrodes, and the lithium ions migrate from the positive electrode to the negative electrode through the electrolyte. The lithium ions insert into the graphite sheets, forming a compound which is the lithium carbon 6. And during the discharge, the ions just go back to the lithium cobalt oxide electrode, and the energy is released using power for an external device. So there is key factors for the storage energy. The capacity, which depends directly on the number of lithium ions that can be inserted in between the graphene flakes. And also, when we talk about power, I mean that the faster this process can be, the higher the battery power is. So, in history, and just to finish on this introduction, so the concept of the first lithium-ion batteries has been started in the 70s, but because at that time we were using lithium metals, we had many
on voit que ton premier slide, comment ça va changer sur le slide qu'on va souhaiter. For sure. Yeah, because otherwise you can do that without or we can try again.
And right now, is that okay?
No, it's just you don't share your screen.
Okay. So I'm starting. So I was thinking, okay. Let's see. Possible storage. Let's start again. Now,
c'est pas en l'écran.
Si je fais un peu l'écran en right now.
Yeah, it seems to be. Yeah, it seems to be. In fact, now we are seeing your screen. So you can see the type of
Ah, il n'y avait pas de souci. Ok. Attends, je change d'écran. Ok.
C'est bon, mais il faut juste retirer. Le présentateur de PowerPoint. Vous voyez le présentateur.
Et là c'est pareil.
Non, on a la droite. Non, on va faire. Oui, c'est ça,
je peux partager le screen.
Merci, Xavier.
I'm sorry.
Because otherwise you can just show the slide.
Juste regarder. Attends, je vais regarder juste de fait. Là, si je fais ça. Donc là, vous avez votre présentateur, c'est ça?
Là c'est pas pour l'écran. Juste l'écran. Ouais, parfait. Nickel.
Là, c'est ok.
Change de slide, non, c'est ça, change. Yeah, it's okay.
No, I'm really sorry on that.
We are outside screen.
Okay, anyway. I mean, I'm sure that you know how to work with batteries anyway, very, without my introduction, but this is not the main. No, okay, so right now with that bag, so I hope that it will be, okay, can I use also my laser pointer? Well, no problem. The main issue I have is if I use the pointer afterward, I cannot switch the slides, which is weird. Is it okay right now?
Yes.
Well, I hope yes. Okay. Okay, anyway, so what I was trying to, I just wanted to give you a very short introduction on lithium-ion batteries. So here is, okay, this is the mature and commercially available batteries, lithium-ion batteries. So you have graphite on one side of electrodes, so giving the charge of lithium and going into like the intercalate in between the graphite, the graphene layers. And here is the other electrode, called the positive electrode, mainly lithium cobalt dioxide. And during the charge, the lithium ions go into the graphite, and the charge they go back to the positive electrode. What I was saying is the key factor is that the storage capacity depends directly on the number of lithium ions that can be inserted in these graphene sheets. And the power is also a very important parameter for batteries, is how fast you can like store those lithium ions in between the graphene. Okay, I will be able to switch. So to finish so that's the next slide. So here is just to give like a very brief historical evolution of lithium-ion batteries. So starting in the 70s, not mature because the use of lithium metals, which creates some safety issues. So we have to wait the 90s. In the 90s, we have a team led by John Goodenough, who started to use a viable and mature battery using graphite electrode as negative electrode, lithium cobalt oxide, and also and check that we had a good reversibility without any safety issues. So actually, since the 70s, not much really breakthrough in the lithium-ion batteries, mainly engineering evolution. So what we can notice that in the early 2000 years, the researchers have been focusing, and industry mainly focusing on the positive electrode. So we started to work on different positive electrodes to try to improve the ion diffusion kinetics of lithium, so to improve the capacity, and also mainly to at the end get very more powerful batteries. And since then, people are mostly right now focusing on two aspects, which is the negative electrodes. This is mainly on what we will be talking today, and also the alternative to lithium-ion batteries, such as both lithium-ion batteries, such as lithium sulfide, but also sodium-ion batteries, etc. So I would say till now, little or no technological breakthrough, but very good, I would say, engineering, trying to improve the first patent from Sony in the 90s. So today we will focus on negative electrodes. So currently in the lab, our research work in the laboratory is mainly focusing on those electrodes. So here on the graph you see the different materials for negative electrodes. So you have here the potential in the y-axis versus the capacity. So the mature battery are using graphite as negative electrode so far, because it has, so to increase the energy you need to have very low potential versus lithium, and graphite has a very low potential. But also what we need is to have a very good specific capacity. So carbon is very mature, but it has quite low specific capacity compared to all those metals such as tin, germanium or silicon. So graphite is used commercially, but silicon theoretically could give capacity which could be 10 times higher than graphite if we could use such materials. So what are the challenges so far on batteries? They are still the same historically, so try to improve the capacity, the charge rate, the cyclic stability, all of those challenges remain on electrodes, even if there is right now a few new, I would say, challenges, and also some practical issues. So what we'll be focusing today and what we are working on in the lab are the use of those new materials for making negative electrodes to improve all of these challenges. So why silicon has a very good advantage? Because the principle is a bit different than graphite. With the silicon, the lithium is not going in between graphene sheets, for instance. It's creating an alloy with silicon. So during the lithiation, we create some lithium X silicon, and we can have like almost 4 lithium atoms per atom of silicon, giving very high capacity compared to the carbon. The problem relies then also on this alloying, because when you make such alloy, you have a 300 to 400% volume expansion of the silicon, which lead to particle pulverization during the use of silicon, and then this enormous volume change create a very short cycle life. Okay, so also silicon has been known for over 20 years as an excellent theoretical candidate for anodes. This mechanical instability has long prevented its integration into viable commercial batteries. So So right now I will try to show you what we did in the lab and how we have developed different syntheses to be able to use those silicon for batteries. So in the lab, we are developing synthesis methods mainly based on electrochemistry, because electrochemistry is not just useful for electrochemical energy storage. In the laboratory, we have developed several synthesis methods, mainly based on electrochemistry. So electrochemistry is a very basic, simple and fundamental process where you have a solution with 2 or 3 electrodes, ion in solution like for batteries, and you can make electrode deposition in this. So you have those ions, you polarize your electrode, and then you reduce the ions to make metals. But you can also strip the metals going back forth and strip the metal to get the metal back to ions. So what we call electrode dissolution. So the principle of electrochemistry is very simple, and in the lab we have been focusing for the past few years on the two type of reactions. So we do anodization of metals to control the formation of metal oxides. I will describe that a bit later, such as titanium dioxide and aluminum dioxide. And we are also doing electrode deposition, growing semiconductors such as silicon, germanium, aluminum, and other type of materials. So electrochemistry is a very versatile and method which is suitable for a wide variety of materials. It's scalable, easy to translate to large scale, which is important for batteries. Very simple. However, it suffers from a big drawback, which is a limitation, which is the electrochemical window of the solvent which is used. So the main limitation rely on the use of water, because when we use water, we have a window which is limited to about 1 volt. So between the water reduction producing hydrogen and the water oxidation producing oxygen. This limitation can be solved by using alternative solvents such as organic solvent, for instance, room temperature ionic liquid. So that's what we've been working on for the past 10 years. So we use mainly ionic liquid that have a very large electrochemical window, up to 6 volts, high thermal stability, very good ionic conductivity, which makes them suitable for electrodeposition or electrodissolution. Non-volatile, quite not high viscosity. And then if we compare, so this on this diagram, we have in this square here is the electrochemical window of water. We see that we are limited to the number of material that we can deposit in water. Let's say copper, for instance, we can deposit copper, reduce copper ions, or strip copper. But we are limited if we use. So here we see all of those different organic solvents. If you use a good combination between the cation and an ion, you can have an electrochemical window close to up to 6 volts, giving us then the possibility of growing silicon, germanium, for instance, different rare earth, aluminum, etc. So that's what we've been doing for the past few years, and I will just show you through a few examples of what we've been doing in using electrodeposition and also electrostripping. So ionic liquids have gained increasing interest in electrochemistry because they offer this promising alternative. So here I will just show you, as I mentioned, what we've been doing on the electrodeposition and electrodissolution. So we've been focusing on developing multifunctional materials in the lab, and particularly silicon for energy storage. I will show you that later, and we discussed already that the silicon is very interesting for batteries. So traditionally, the silicon is deposited using vacuum methods like CVD or PVD at high temperature, often using catalysts like gold droplets, for instance. But however, electrochemistry in carefully selected ionic liquid also allows silicon deposition at room temperature. So here we have a CV diagram. So you have the current versus potential using silicon tetrachloride as a precursor. And we see like during a two-step process, so we have first the reduction of silicon 4+ and silicon 2+, and then the production of silicon. Water would be limited versus platinum at -1 volt, so here we would not be able to deposit to reduce such ions in water, of course. So we see here on the right side, we have some bulk silicon electroposition. So we have like two SEM images showing that we can, by adjusting the synthesis parameters, potential, current temperature, it is possible to control the morphology. So here we have, for instance, the possibility of having some laminar growth or columnar growth of the silicon just by adjusting the parameter. Okay. So I will just get the process. Okay, so we can also use of course silicon templates to go, for instance, use photoresist to grow the silicon, and after removing the photoresist, we have some silicon, for instance. Here is like silicon dots, which is like submicronic dots. We can also cover, if the support is sufficiently conductive, we can grow silicon on top of nanostructures, nanocones, for instance. So here we have by reactive ion etching and morphology of silicon, crystalline silicon, and then we can grow silicon deposit on top. As I said, we can also, for instance, grow rare earth, for instance. So here we try to also do some doping on the silicon. So we use erbium and terbium precursors. So it gives us the possibility, which is mostly normally obtained by say ion implantation. Here we can grow co-deposition of silicon and those rare earths, giving us different possibility of having different content of those rare earths like terbium or erbium. Here, for instance, it's some like optic characterization, photoluminescence and cathodoluminescence measurements confirming the presence of terbium on silicon. This is EDX showing how homogeneous it can be. Okay, we can do also anodization. I will just show that briefly. because I would like to talk about batteries. So this is all kind of metal we can anodize to create those oxide and to do the structuration. So it is a reverse. We are not reducing ions, but we are making oxides. Mainly today I will focus on the titanium, which is we start with the titanium foil and then we anodize to make those nanotubes. So the principle is the same, but we just try to create an oxide. So here we mainly work in diethylene glycol with some content of water and HF. So it's a two-step process. First you create titanium dioxide, and then we have a chemical dissolution of this oxide to create the pores. By adjusting the parameters, you can control, you can go from a porous membrane to structuration to get some nanotubes, some nice nanotubes like that. So here is the titanium foil. After anodization, we have the titanium dioxide. Okay, so the purpose, so this is what we can do using organic solvent. And the purpose of my talk is really focusing on those lithium-ion batteries. So as I mentioned in the introduction, silicon is very interesting, but like germanium, like tin, but creating those alloys, when you charge and discharge the electrodes, it creates, it breaks the materials. So how to overcome this problem? There is two strategies. One is to create nanostructuration, and the other one is to work on composites. So we tried in the lab to create, in the past, a nanostructuration of the silicon by growing some interpenetrating network of silicon. So if we had a quite good capacity, very promising, but the material cycle life was limited due to the poor electrical contact between the silicon and the current collector. So then we switched to, so that would be the main interest right now of the technique we have developed. So we switched to composites. So we decided to create composites made of two kinds of materials. One, which is the titanium dioxide, which is a template here, conductive template, which is not also a dead mass because TiO2 can be lithiated. And then we cover the TiO2 with some silicon. The purpose of the TiO2 is to maintain the mechanical expansion during the charge and the volume expansion of silicon during lithiation. So here we see that we start with the anodization of titanium foil, and we saw earlier, and then we do an electrodeposition on top of the TiO2 to create those composites. So TiO2 creates a very good buffer for the volume expansion, providing also an extra capacity, because TiO2 is very relevant also for lithium-ion, for high-power lithium-ion batteries. And the silicon, thanks to this TiO2, perform very well with a very good cyclic performance. So here we have the capacity, that is the second number, and we see that the efficiency is very good. We are very close to 95% efficiency. And then the capacity retention, which is dropping to L4 depending on the quantity of silicon that we have. So how to improve this? This is on what we are working right now. So two aspects. We can all improve the material. So here I just show the silicon, but as I said in the electrodeposition, we can make alloy. But also we need to increase the active mass. So to increase the amount of silicon deposited, we need a larger and porous structure that we can use, larger than the TiO2. So we did work on different materials, still using TiO2 to see how to improve the silicon we make by electrodeposition. One way is, for instance, to create an alloy with the silicon, because silicon is not well conductive, which is a drawback for negative electrodes, because the lithium has to be reduced inside the silicon. So then we create some alloy. So we try to alloy silicon and germanium, but also silicon and aluminum. So we see some here depositing aluminum, for instance, on TiO2. Here we can grow germanium, silicon germanium, so we try different kind of materials. And then also to increase the amount of silicon, we try to change the template. Instead of using TiO2, And for instance, we are working right now on the Ti3C2 Maxins template. Just few results. So here is few last results. So that is aluminum to silicon. So we have this showing that we can grow silicon aluminum on top of TiO2. The amount of aluminum can be controlled by the electrochemical parameters, so we can control the aluminum content inside the silicon, and this low amount of aluminum is enough to improve the electric conductivity. And then we see on this graph right here, we have the capacity versus the number of cycles, and the C represents the current used to charge or discharge the battery, and 2C is very high current, C over 10 is very low. And we see that when you add on the red here some aluminum, because the conductivity is much higher, we have a much better capacity. So we try to work still on the alloying, making materials more promising for battery, and finally to try to switch to have a higher silicon and to have a mature negative electrode for lithium-ion batteries. We try to also create new composites using 2D materials, because it gives us the possibility of having a easily large-scale process for making batteries. So what are Maxins? In 2 words, Maxins are, we start from a ternary compound, which is Ti3Lc2, and then we do etching on these aluminum to create those non-exfoliated sheets. And then we can collect those sheets to create a slurry made of these Ti3C2. So the goal is to transfer what we have, the proof of concept we had on the TiO2 into these Maxins. So that is very recent work that we have done in the lab. So we start with these Ti3Lc2, then getting those non-delaminated Ti3C2, and then we get those little flakes. We can, using those flakes, make some slurry. So that is, again, this is the same material. So we have a dry, exfoliated Ti3C2. Then we can make a slurry, which gives us such a crumbled Ti3C2. Purpose is to transfer what we did on the TiO2 to on the Maxins. So here we grow some silicon. This is very preliminary results we just published on the growth of silicon onto the Maxins to create mature negative electrode for battery. So that's it. So here we see the lithiation, and the process seems to work very well. Silicon is conformally deposited into the Maxins. Quite good capacity of silicon on top of these materials. So sorry for the difficulty in showing my slides, so thank you very much for your attention. A few acknowledgements. I acknowledge Mahatma, which is the Director de Recherche of the LRCS, for his precious discussion on the battery issue that we were facing, and all those PhD students and doctors I've been working with. Thanks for your attention, and sorry for the little problem I had during the presentation. So,
thank you, Dr. Jeremy, for the information.
Jeremy, thank you very much joining online for this workshop. I have a very small query with regard to the stability of the electrode, the silicon or germanium what you use. How many cycles you will be able to perform with this type of electrode materials?
Actually, we have still some. We still have some battery running right now. So most of the time we cycle. We are still batteries under charging right now. But we did most of the time before publishing it, it's try to have like 100 cycle minimum. Then at least 100. When we have regarding the silicon and TiO2, we have a battery already almost 1,000. We have 80% efficiency after 1,000 cycles.
And with regard to the vaccines, what you have mentioned, the number of layers, were you able to control the number of layers?
Oh, sorry, I cannot hear you very well. So regarding the vaccines, you say?
Yeah, vaccines.
What is
The number of layers.
what are you saying?
How do you control the number of layers?
Which layers?
Vaccine layers. Vaccine layers.
So actually we work because the problem of vaccines most of the time, I can show that maybe on my presentation, the problem of vaccines is to be stacking. So the problem of vaccine, when you use vaccines most of the time, you have restacking of the flakes. So we did work in some chemistry to change the charge of the surface to have a crumble structure, because most of the time when we use, I don't know if you see the slides right now, but most of the time the problem of vaccines is that you have a restacking. And then right now we try to work by different methods. I can show you one here, which was not efficient actually, but we try to modify vaccines to disease vaccines, and we use to create cell pressure. For instance, at the beginning we use styrene beads, but that was not relevant because the styrene beads were not electrical conducting enough. So then we use some more different actually chemical treatment. So we have a thickness of right now 100 micron porous Ti3C2, which is enough for making negative electrons for battery. I don't know if I replied to the question because it's difficult to understand perfectly. But
Yeah, thank you very much. Thank you.
Long live India and France friendship.